If you watch an asymmetrical object like an asteroid as it tumbles freely through space, its axis of rotation constantly shifts and wanders. To track this motion mathematically, physicists look at angular momentum. For a single point of mass, angular momentum is the cross product, a type of perpendicular multiplication, of the particle's physical position and its straight-line linear momentum. When you add up all those particles for a whole object, you run into the 3D problem. The direction the object is actually spinning, represented by the blue angular velocity arrow, and its total angular momentum, the red arrow, do not point in the same direction. As the body rotates, that angular momentum vector wobbles and precesses. Because the orientation is constantly shifting in space, you cannot use a single value to describe the spin. You would have to calculate every coordinate change for every microsecond of the motion. To predict the motion of everyday objects without tracking those three-dimensional shifts, we need to introduce a physical anchor. Imagine taking that tumbling object and driving a rigid rod straight through it, locking it to an immovable line. We'll call this the z-axis. With that rod in place, every single particle inside the body is now forced to travel in a perfect circle, locked into a flat plane that sits at a right angle to the axis. Imposing this strict physical constraint allows us to drop the complex three-dimensional wobble and isolate the motion to a single, highly predictable dimension. We can take that total angular momentum vector and project it onto our coordinate system to see exactly what pieces it is made of. First, there is the component that lies perfectly parallel to our fixed axis of rotation. We denote this vertical shadow as L sub z. Then there is the rest of the momentum, the component sticking out sideways, perfectly perpendicular to the axis. As the object spins, that perpendicular component just sweeps around in a flat, predictable circle. Its size never changes. Because our object is securely mounted to a fixed axis using hinges or pivots, those physical mounts actively push back and cancel out any changes to that sideways component. The hinges are doing the hard work of handling the perpendicular momentum for us. That means we can safely drop it from our calculations and write our equations using only the vertical momentum aligned with the axis. To change an object's angular momentum over time, you have to apply an external twisting force. We call this twist a torque. Looking at this equation, the angular momentum along the axis is equal to the moment of inertia, I, multiplied by the angular velocity, omega. Moment of inertia is simply a measure of how spread out the object's mass is from the center. To see how the object accelerates, we take the derivative of this equation with respect to time. For a solid, rigid body, the moment of inertia does not change. The mass stays exactly where it is. That means the only thing changing over time is the angular velocity, giving us the angular acceleration, represented by alpha. The 3D geometric complexity has resolved into a direct proportion. We are left with a relationship where the applied torque drives the angular acceleration, scaled entirely by the object's moment of inertia. If you remove all external twisting forces, meaning the torque is zero, the total angular momentum locked along that axis must remain perfectly constant. You can observe the relationship between mass distribution and spin speed directly using a swivel chair. By pulling their arms in, the person decreases their moment of inertia. Because the total angular momentum is conserved and cannot change, the angular velocity mathematically has to increase to keep the equation balanced. This simplified fixed-axis math allows us to reliably predict the motion of everything from a spinning figure skater to heavy industrial machinery. We started with the chaotic, tumbling geometry of an object in free space. By pinning it to a single axis, decomposing the vectors, and letting the physical hinges absorb the sideways forces, we isolated a clean, scalar law. In physics, constraints are often the exact tools we need to strip away the noise and uncover the precise mathematical rules governing how objects actually move.